Introduction. This is a book about the human body understood as an electrical system, and it means that claim in the plainest possible way. Not as a metaphor, not as a mood, and not as the opening move of a sales pitch, but as a description of what a body physically is. Every living cell holds a voltage across its outer membrane. Nerves, muscles, and the heart do their work by moving charge. And the whole organism lives immersed in the electrical environment of a planet that has its own fields, currents, and rhythms. The pages that follow take that fact seriously and follow it in one long, patient direction, outward from the single cell to the biosphere and then back again, without either inflating what is known or dismissing what is merely unproven. Because the subject sits on a border where careful science and hopeful speculation are so often sold in the same package, the book keeps a strict rule about evidence and states it at the outset so the reader can hold the author to it. Claims are sorted throughout into categories: established science that is mainstream and well replicated, primary measurement whose interpretation may still be argued, the historical and interpretive literature that shaped how people came to think about the body electric, and frankly, speculative frontier material, included because it is interesting and labeled plainly as speculation rather than fact. The early chapters live almost entirely in the first of these. That is deliberate. Before a book can responsibly discuss grounding, structured water, biophotons, or solar storms, it has to earn the reader's trust by getting the settled science right. Only once the foundation is secure do the later chapters move toward the edges, and when they do, the mainstream view always stands beside any minority or speculative claim. The book opens, as it will also close, on a beach, with an article resting on a reader's knees, and a question it will not quite put down. From that quiet scene, the argument descends inward until it reaches the thing everything else is built on. The first part, the electric cell, begins with the discovery itself. Galvani's twitching frog leg in the 1780s, Volta's skeptical reply, and the long instrumental campaign that ended in 1952 with Hodgkin, and Huxley writing down the mathematics of the nerve impulse. From there, it settles on the central fact of the whole enterprise, the small, steady voltage a cell maintains across a membrane a few billionths of a meter thick, and it shows how the traffic of charged ions across that membrane becomes the language every cell uses to signal, contract, and think. With that foundation in place, the second part turns to the body's most conspicuously electrical organs. The brain is examined as a genuine electrical instrument, its synchronized cellular rhythms faint enough to require careful amplification, yet strong enough to be read through the skull. The heart is shown timing its own beat with an internal current whose signature can be recorded from the surface of the skin. These are not exotic claims. They are the daily bread of clinical medicine, and the book leans on them because they establish beyond argument that the body is electrical in ways that can be measured and trusted. The middle parts widen the view from organs to the whole surface and structure of the body. One part follows the skin, the static charge a body can carry, the small standing voltages of living tissue, and the popular practices of grounding and earthing, weighing what the measurements actually support against what has been claimed for them, and extending the same scrutiny to hair and nails. Another part moves beneath the skin into the connective tissues long dismissed as mere packing material, the fluid-filled interstitium and its role as a communication matrix, and the collagen and fascia whose fibers generate small electrical signals when stretched or compressed, a genuine piezoelectric effect that gives structure a voice in the body's electrical life. From tissue, the book moves to the two media through which so much of that life is conducted, water and light. It treats water first as the ordinary indispensable solvent of biology, then turns to the more contested frontier of exclusion zone or structured water, setting the specific measurements and the strong reasons for caution side by side. It examines the ultra-weak light that living tissue genuinely emits, distinguishing the real, faint biophoton signal from the larger meanings sometimes hung upon it. And it looks at the eye as an organ that both absorbs light and takes part in the body's exchange of photons and charge. Having built the body upward from membrane to surface to medium, the book then sets that charged body inside the charged planet it inhabits. A central part surveys Earth as an electrical environment in its own right. The fair weather voltage of the atmosphere, the magnetic field generated deep within the planet, the Schumann resonance that rings in the cavity between ground and ionosphere, and the disturbances the restless sun sends through it. Here the book is at its most careful, because here the temptation to overreach is greatest. It reviews what the evidence says about magnetic storms and human health, about possible links between solar activity and mood, and about the added exposures of high latitude, high altitude, and polar flight, reporting the mixed and often thin findings honestly and letting the uncertainty stand where the data leave it. A further part narrows to rhythm and resonance, weighing the brain's own wave states in meditation and whether geomagnetic conditions leave any measurable trace on brain activity. The final part gathers everything. It draws the body as a single matrix of conductive and responsive tissues rather than a bag of separate electrical parts, and then, in a deliberate act of discipline, examines the limits of its own central metaphor, asking where the language of charge and field genuinely describes the body and where it only decorates it. It closes by sorting the whole subject plainly into what is established, what is promising, and what remains speculative, before a short conclusion restates the thesis in a single breath. The body is electrical from within, the world is electrical without, and the two are made of the same physics, with no separate electricity for a body and another for the sky. That thesis is the whole of the book, and its two halves must be held together to be seen clearly. A short epilogue returns to the beach where the first chapter began, stepping for a single page out of the careful register the rest maintains, back to the person with the journal and the question that would not leave him alone. Everything between the beach and the beach is an effort to establish each half of the argument honestly and to say, with equal honesty, exactly how far the continuity between them has been shown to reach. The aim throughout is the plain, patient voice of good science writing. Define the terms, respect the reader, keep what we know distinct from what we suspect, and let the real phenomena carry the wonder which they prove more than able to do. Part 1. The electric cell. The foundation, the body as a bioelectric organism, and the membranes and ions that make every cell a tiny electrical device. 13. Part Y. The electric cell. Chapter 1. The body as a bioelectric organism. I let my gaze drift from the page back to the water. The afternoon kept moving around me, but more softly now, as if the beach had receded just enough to make room for thought. The sun remained on my skin, gentle and steady, and I had the strange impression that it was doing more than warming me. It was meeting me, touching the body in a way that felt almost instructive, as if light itself were a quiet kind of shaping force, not rigid, not mechanical, just a persistent warmth that seemed to gather the body into coherence. The article in my lap stayed open where I had left it, its claims hovering in the mind like unanswered questions. Radioactive decay, solar flares, neutrinos, A pattern in the data, maybe, or maybe only a pattern in our hope to find one. I could not stop thinking about the possibility that the body, too, might be listening to the same larger rhythms, that the Earth's magnetic field and the sun's changing activity could be brushing against us in ways we barely understand. There was something unsettling and beautiful in that idea, as if life were not sealed away from the universe but threaded through it, responsive to currents too subtle to name. That was the deeper question, the one behind the headlines and the measurements, not simply whether solar flares affect humans, but whether the human body is already participating in the same field of influence, the same hidden exchange. If telluric currents move through the Earth, and if geomagnetic storms disturb the planet's electrical environment, then what is the body doing inside that system? Maybe headaches are only headaches. 14. Maybe they are weather. Maybe they are the nervous system responding to a storm too faint for language, but not too faint for flesh. And still, the uncertainty did not feel empty. It felt alive. Because even if the evidence is mixed, even if large studies have found no clear correlation between geomagnetic activity and headaches or migraines, the question itself points toward something real. That human beings do not exist apart from the larger environment, but inside it, in constant exchange with it. The body is always receiving, always adjusting, always translating light, heat, and invisible forces into sensation. Standing or sitting still does not mean being unchanged. It only means the changes are quiet enough that we have to listen differently. The wind moved across the sand, and the ocean kept shimmering beneath the noon light. I held the magazine open in my lap and felt for a moment as though I were holding a doorway rather than a page. Outside me, the world was all sun and salt and motion. Inside me, the questions kept turning, slow as tides, asking whether we are ever truly separate from the star that made us possible. That is the intuition this book begins with, and also the one it refuses to take on faith. The exchange between the body and the wider world is real in a strict physical sense. The difficulty is that the moment a description reaches for something grander than the evidence will bear, it stops being science and becomes longing. The discipline of the pages that follow is to hold those two apart, to take the question seriously enough to test it and to say plainly wherever the testing runs out. And that testing has a beginning older and humbler than any talk of solar storms. Before anyone could reasonably ask whether the sun stirs a human mood, someone first had to establish the plainest fact underneath all the rest, that the body is electrical at all. That story does not begin on a beach, and it does not begin with the sun. It begins with something much smaller and much stranger on a dissecting table more than 2 centuries ago. On a working table in Bologna sometime in the 1780s, a dead frog moved. Its legs had been skinned and its lower body separated from the rest, and yet when a metal instrument touched the exposed nerve at the 15th moment, the muscles contracted as though the animal were briefly, impossibly alive. The anatomist watching this was Luigi Galvani, and the twitch he saw would take more than 1.5 centuries to explain. Galvani believed he had found a special force carried within the tissue itself, a kind of electricity that belonged to living things. He called it animal electricity, and he was closer to the truth than almost anyone realized at the time. The claim that the body is electrical can sound to a modern ear like the beginning of a sales pitch. It is worth saying plainly at the outset that it is nothing of the kind. That the human body runs on electricity is one of the most thoroughly established facts in all of physiology. It is taught in every medical school, measured in every hospital, and used every time a cardiologist reads an electrocardiogram or a neurologist orders a recording of the brain. The body is not electrical as a figure of speech. It is electrical in the same literal sense that a circuit is electrical. Charges move, voltages exist, and those voltages do work. This chapter introduces that idea and follows it in one direction only, inward and downward, from the whole body to the organs, to the tissues, and finally to the single cell, where the electricity begins. Later chapters will move outward again, toward the skin, the connective tissue, and the electrical environment of the planet. But everything in this book rests on the foundation laid here, and the foundation is small enough to hold in the mind, a thin membrane, a difference in charge across it, and the movement of a few kinds of ion. 16. Figure 1. The action potential, the self-propagating voltage spike that carries nerve and muscle signals, driven by the time flow of sodium and potassium ions. Credit original diagram created for this book. The discovery that the body runs on electricity. Galvani published his findings in 1791 in a Latin treatise whose title is usually shortened to the Commentary on the Effect of Electricity on Muscular Motion. He had noticed that a frog's leg muscles would contract when a nerve and a muscle were connected by an arc of two different metals, and he concluded that the tissue stored an electrical fluid of its own. Discharged through the metal like the discharge of a Leyden jar, it was a bold and, as it turned out, only partly correct interpretation. His most formidable critic was Alessandro Volta, a physicist of the first rank. Volta argued that the electricity did not come from the animal at all. It came from the junction of the two dissimilar metals, and the frog's leg was merely a sensitive detector, a moist and delicate electroscope registering a current made elsewhere. To prove the point, Volta built, around 1800, a stack of alternating metal discs separated by moist pasteboard, the voltaic pile, the first true battery, which produced a steady current with no animal tissue anywhere in sight. It was one of the pivotal inventions in the history of science, and it seemed to demolish Galvani's idea. 17. The irony, resolved only much later, is that both men were right about something. Volta was correct that a junction of dissimilar metals generates a current, and that this artifact had contaminated many of Galvani's experiments. But Galvani was correct that living tissue produces genuine electricity of its own, independent of any metal. The word we still use for stimulating a muscle electrically, to galvanize, keeps his name alive, and so does the fact that his central intuition survived his critics' brilliant objection. Through the 19th century, the case for real animal electricity was built instrument by instrument. Émile Dubois-Reymond, working in Berlin, developed galvanometers sensitive enough to detect the faint electrical change that sweeps along a nerve or muscle when it is active. In 1843, he described this traveling disturbance, the signal we now call the action potential. By 1902, Julius Bernstein had proposed a physical explanation, his membrane theory, which held that a cell's resting electrical state arose from a membrane selectively permeable to potassium. Bernstein was almost right, and being almost right in the correct direction is how much of science advances. The full account arrived in 1952 when Alan Hodgkin and Andrew Huxley published a set of equations describing exactly how the action potential is generated by the timed movement of sodium and potassium ions across the membrane of a nerve. They had worked on the giant axon of the squid, a nerve fiber thick enough to probe with the electrodes of the day, and their model was so precise that it still forms the backbone of neuroscience. The work earned a share of the Nobel Prize in Physiology or Medicine in 1963. From a twitching frog leg to a system of differential equations took a century and a half, but the destination vindicated the traveler who set out first. 18. Luigi Galvani, 1737–1798, who found that a nerve muscle preparation could be made to twitch by electricity and proposed the idea of animal electricity. Credit public domain via Wikimedia Commons. A plate from Galvani's 1791 treatise showing the frog leg experiments on which the science of bioelectricity was founded. Credit Luigi Galvani, 1791. Public domain via Wikimedia Commons. 19. Alessandro Volta, 1745 to 1827, whose voltaic pile produced a steady current with no animal tissue at all. The objection that sharpened Galvani's discovery. Credit. Public domain via Wikimedia Commons, ETH Bibliothek Zurich. 20. A schematic of Volta's pile, alternating disks of two metals separated by moist pads, the first source of a steady electric current. Credit. Vector Voyager, translation, CC by SA 3.0 via Wikimedia Commons. Giovanni Aldini, Galvani's nephew, who staged dramatic public demonstrations applying current to animal and human cadavers. Credit. Unknown author, CC by 4.0 via Wikimedia Commons. 21. The voltage every cell keeps. To understand why the body is electrical, begin with the smallest unit that is. Every living cell is enclosed by a membrane, and across that membrane there is a voltage. In a resting nerve cell, the inside sits at roughly 70 thousandths of a volt below the outside, written as about minus 70 millivolts. The number is small, but the scale on which it operates is smaller still. The membrane is only a few billionths of a meter thick, so that modest voltage spread across so thin a barrier produces an electric field of enormous intensity, comparable to the field near a bolt of lightning. Each cell, in this sense, holds a charged boundary under remarkable tension. This voltage is called the resting membrane potential, and its most important feature is how widespread it is. It is not a specialty of nerve cells. Muscle cells have it, and so do the cells of the liver, the skin,